Video number 2. So now we're going to talk a little bit about triangles. So any equilateral figure means all the sides have the same length. So if I take 3 equal length straws, and I run a PCR and through it and tie it tight, it turns out that forces an equal angular triangle as well. There is no way to shift the 3 equal straws without bending one of them. So an equilateral triangle, all sides have the same length, and all the angles end up being the same. So the angles measure 60 degrees each. Now, an isosceles triangle is a triangle where 2 of the angles measure the same. And then the cool thing about triangles is the sweep, the measure of the angle, also determines the length of the side across from it. They're proportionate. So bigger angles get bigger sides, smaller angles get smaller sides. So the 2 sides opposite these angles are also equal. Now, a lot of people, when they draw these triangles, it kind of like ends up looking equilateral. So I'm going to deliberately draw a very isosceles but not equilateral triangle. So if we put a line like this, we usually try 1. So I'm trying to make it so this angle and this angle are the same. And if that is the case, then that side and that side. So the left and the right here, those long sides are equal. We could actually use that to our advantage and do some fancy stuff in some figures. All right, scalene, like it's a term we use right now, and then it never really shows up again. So this is a triangle where none of the angles are obtuse. Now, sometimes they'll say it's, or all the angles are acute. So the first one would allow a right triangle to count as scalene. I'm trying to remember. No, that's not it. It's not where none of the angles are obtuse. That would be an acute triangle. All right, so all 3 angles are different measures. So all 3 sides are different lengths. Sorry, was trying to remember a definition from 30 years ago. All right, the triangles we actually use on a regular basis are right triangles. We like right angles. Those form some of the most supporting structures. And also a right angle is how we determine our area on figures. We need to see a right angle, so we've got a length and a width, or a length and a width, or the breadth and the depth, base and the height. It's always a right angle. Now it can only be one angle, because if 2 of the angles were 90 degrees, it's not a triangle, because these sides can never touch, because once I try to make them touch, one of the angles is now no longer 90. Now in foo-foo fancy crazy geometries that are not restricted to the plane, a flat piece of paper, you can manage a triangle with more than one right angle. Like on a globe, you could draw 3 right angles and have straight lines connect them, but they're straight on the globe. It's kind of weird. All right, so for this, there we go. So that is also a scalene triangle because I made, this is our short side. We'll call that A. Then this is our medium side. We'll call that B. And then the big one across here, which often gets labeled C. This is our funny hypotenuse. And one of the reasons we talk so much about right triangles is because the sides interact very, very nicely. This is our good old Pythagorean theorem. A squared plus B squared equals C squared, where the one on the right side is the hypotenuse, the longest side. A and B, if you mix those two up, it's fine. But if you put either of those in the C spot, doesn't work. You're going to solve for the wrong thing. Now, a special note about triangles is that all of the angles in any triangle you draw, as long as it's on a flat plane, all of those angles add up to 180 degrees. So one of the things I like to do, and if you've got like a niece or a nephew or a kid to play around with this, like you have them draw a triangle and you cut it out and then you rip each of the angles off and then you put them together with all the vertexes together and it'll make a straight line, assuming you cut it straight and not wibbly wobbly. So like anyway, as long as you rip the full angle off, it'll line up. It looks really cool. It's one of those, like, you can, I wonder what's going to happen. Is this going to work for all triangles? Could we draw some more triangles and figure it out? And, you know, that's not a rigorous proof, but it is a, let's investigate the thing and see if we can come up with a thought, a hypothesis, different from a hypotenuse. All right. So how do you find the perimeter of a polygon? So the perimeter or perimeter, I'm saying it like that because it has the word meter, meaning this is a distance. So the perimeter is the distance around, which means you add all the sides. You can also think of, like, you know, in movies where they're like, scan the perimeters. They're looking at the edges. Now, a circle is a little bit more interesting. It does have a perimeter, but it gets a special name because it's not a bunch of sides. It's just one smooth curve. So I'm going to put it in quotes here. The circumference. So that is, if I draw a circle and then I take a string, I go all the way around and then I pull that out and measure it, that is my circumference. So it is a distance I can measure. It is just not made up of straight lines. And then the area of a shape. I like to think of this as how much paint it would take. So if you were going to paint a piece of paper, the measure of the area, you could convert that into how much paint you would need. It's very often how it shows up in problems. All right. So perimeter is the distance around, area is the space the figure takes up, I guess. It's a two-dimensional measure. So area, perimeter, or circumference are going to have like meters. Hold on, let's get a real pen. So this might be measured in meters or inches or feet. Same for circumference, but area is going to be measured in square meters or square inches or square feet. And sometimes, like in more normal settings, people write SQFT instead of the feet squared, which I think is actually just a holdover from when typing squareds was more difficult, like on a typewriter. But that's the idea. All right, so we're going to fill in here our handy dandy cheat sheet of formulas. So the perimeter of a circle. There's two ways to write the circumference formula. So one of them is C is pi times the diameter. But it could also be written as the diameter, remember I said was two radiuses put together. So if I take the length of one radius and double it, I get the length of the diameter. So sometimes we write this as 2 pi r. Either of those works. Now just remember pi is r, two lines with the squiggly on top, and the decimal approximation, the one we usually use is 3.14. This is because, you know, if you're pulling this out to try to figure out how much paint do I need to buy to cover this thing, or, you know, how much ribbon am I going to need to buy to go all the way around this? 3.14 will get you close enough that you're good. In foo-foo math terms, like on your graphing calculators, even on your scientific ones, there's a button for pi, and it puts a ridiculously long decimal. Pi itself is irrational. It goes on and on and on and on. So it's not just 3.14. The next few numbers are 159, then it's 2, and then I never remember the number after that. So for circles, pi comes into play. Now, the funny thing is pi is actually defined as the ratio of the circumference over the diameter, which if I solved this first circumference formula for pi, that's what I'd get. So the circumference formula is actually like strangely, I don't know, it kind of came around backwards, I guess you could say. All right, and then area, the area of a circle. All right, I'm going to write this one. The area of a circle is pi r squared. Pi r not square, pi r round, cake r square. It's a dumb dad joke my dad told me when I was in geometry. So I'm sharing it with you in his memory. But pi r squared. Area, you should see a distance times a distance in some way, shape, or form in the formula. That's what gives you an area. You look back at pi times diameter, there's only one measure, diameter. Pi is just a naturally occurring constant. It doesn't have units. Likewise, the 2 times pi times r. R is the only distance there. The 2 is a constant being put in there. It doesn't have any units. So down here on the square, if L is my side, then the perimeter of the square is, there are 4 of those, so we would say 4 times L, or length. That's my cursive lowercase l, because if I just draw the straight line, it confuses everyone. This is why I usually just draw the capital. And then the area, in this case, since we know a square meets with a right angle, it's just the length times the other length. So L squared, or, you know, if you want to write it with S or you want to use the capital L instead, feel free. I'm just trying to stick with what they wrote in the figure. So our rectangle down here with the length and the width. So the perimeter, we're going to add that up. So now I've got 2 different lengths. 2 of them are lengths. I'm going to go with capitals now. And 2 of them our widths. So 2 times the length plus 2 times the width would add up all 4 sides. Likewise, the area, the length and the width meet in a right angle. So I multiply those two and there's my area. L times W. So it's always the two things that meet in the right angle. Those are the things you're going to use in your area formula. You may have to put some extra things in there, but that's what you need. Now a parallelogram. So there's a length, a width, and a height here, just to be weird. So our area is going to come from the length times the height. Now, what I like to think of this as is it's a tilted rectangle. So if I think of my rectangle, now bear with me here, it's kind of weird, but if I think of my rectangle as like a whole bunch of paper stacked on top of each other, and then I put my hand on the side and kind of push it along so all the pages lean, like slide over a little bit, I still have my same like width of the paper, and the length of my sides has changed. So the perimeter has changed, but the area that's being covered by that on the end is still the same. I just slid all the line segments over at an angle, but the area being covered is identical. So if I shifted it all back, so now my height is the thing that we're calling the width, same area. So don't know if that helps or not. I found it a useful thought when I was trying to figure out how the heck this figure worked. All right. But the perimeter is going to be the same as the rectangle, the 2 L's plus the 2 W's. Just add all the lengths of the straws. And then our lovely triangle. So perimeter here again, add all the sides, ABC, with pluses, not A times B times C. So A plus B plus C. Now, the area. I get this question sometimes where people are like, all right, I know the area is 1/2 base times height, but which one's the base? And some of you might be like, oh, that's a silly question. You say that now, and then you start taking a test and your brain goes, boop. So don't ever say a question is silly. Everybody asks a question for a reason, even if the reason is to make fun of the person they're asking the question to. There's still a reason. Usually, though, the reason is the teacher didn't explain it right, so they need to do better. All right, I'm going to make that a big B. It is not the side called B in the figure. This is B for base. Just like I was saying before with the length and the width and the length and the height, the things that have the right angle in between them, which in this figure is C. So the height and C form that right angle. Those are the two things I want to see in my area formula. And then a triangle is half. If I made this into a rectangle, it would sweep up the whole side. And the triangle cuts each of those sides in half. So that's why we have the half in there. Yeah, I know you're getting really weird proofs and way more information than you needed, but blah, formulas. All right. Then we've got some quick like calculation crunch questions, just practice that we'll run through in the next video.